So just kind of recapping where we were on Thursday. We were looking at molecular compounds and we were looking at the naming systems associated with those compounds. And we said that structurally speaking, the naming was exactly the same. We're going to name the first element first. We're going to name the second element last. We're going to change the ending of the second element to IDE. The only thing that was going to be different, really, was the introduction of those prefixes. And we had 10 different prefixes that we could use. And we looked at those 10 prefixes here. And so then we did a couple of examples. And so to kind of get us back into the proper frame of mind here, let's go through and do some more examples of naming just to kind of refamiliarize ourselves with it. And then we'll get into kind of the last parts here of chapter 6. So in letter A, here I know I have carbon and I have oxygen. Now I have one of each of those. And so the prefix for one is mono. On the first element, that's implied, so I don't need monocarbon there. I just need carbon. For oxygen, we're going to change that from oxygen to monoxide because we need to add the prefix and we need to change the ending to IDE. And so the name of this compound would be carbon monoxide then. In the second compound, we've got nitrogen and oxygen. Those are the two elements. Again, the nitrogen only has one. Prefix for one is mono. The mono is implied here because it's the first element. I had oxygen, but I'm going to need to change it. I've got two. Two is di. So my prefix is di, and I need to change oxygen to oxide. Nitrogen dioxide is the name of this compound. Third one, I've got phosphorus and fluorine. Prefix for phosphorus would be mono, but since it's the first element, again, that's implied. Fluorine, I need to change its name. I've got three of them. Prefix for three is tri. And I'm going to change fluorine to fluoride. So this would be trifluoride. And so the name of PF3 is phosphorus trifluoride. The last one, I've got carbon and I've got chlorine. Carbon, again, one, the one's implied, so we're not going to change carbon at all. I need the prefix for 4. I can look at my sheet here. Prefix for 4 is tetra. So chlorine gets changed to chloride. And we add the prefix tetra. So this would be carbon tetrachloride. All right, any questions with these four? I will tell you, once you get used to the structure of it, molecular naming is way easier than ionic naming because you don't have so many rules and kind of special situations. You don't have to worry about charges. You don't have to worry about, you know, balances. The name of the compound reflects the formula. All right, try this one yourselves here. I've got diboron trioxide. So what you want to think about is, what do those prefixes mean? What are the elements that they are coming from? So at the root of diboron, we would be talking about boron, which is B. At the root of trioxide, we're talking about oxygen, which is O. So we know that this compound is boron and oxygen, B and O. Now it's just a matter of the prefixes. Diboron is 2 borons. Tri would be 3. So the compound here would be B2O3. And so it doesn't matter if I'm going one direction versus the other. I should be able to very quickly tell from the name what the formula is. That's the real nice thing about molecular compounds. All right, quickly. 90 seconds. Give me the 3 formulas for these 3 compounds. If you're unsure of the prefixes, that's why I gave you the page here. So penta is 5. Phosphorus pentachloride would be PCl5. Dinitrogen tetroxide, or excuse me, dinitrogen trioxide, that'd be 2 nitrogens, 3 oxygens, N2O3. Sulfur hexafluoride, have to know that hexa is 6, so SF6 would be the correct answer there. All right, we okay? Any questions? Okay, so let's get away from naming then. Let's just kind of talk about the differences between the 2 kinds of compounds. So how do I know I'm looking at an ionic compound or a covalent compound? So if I just give you a chemical formula, can you quickly tell from that formula what it is? And knowing the difference between ionic and covalent compounds, can you kind of get some ideas about, okay, I would expect this to be a solid, I expect this to be a gas, those kinds of things. So how do I tell if it's ionic? Well, your book says ionic compounds usually start with a metal. Yeah, that's pretty much the best way to tell. It does get a little bit confusing if you have the ammonium ion, just because that that would mean that there are no metallic substances in the compound at all. The other way that you can look for is if I'm looking at the chemical formula of the compound, ionic compounds almost always have metals and nonmetal elements in them. Compounds are covalent if the first element in the formula is a nonmetal. Another way of thinking this and phrasing this is that I've got two nonmetal substances together, or multiple nonmetal substances together. And for the sake, and this is written on your nomenclature guide that I gave you, the other thing that we have to remember is that for the sake of naming and identification, metalloids are going to be more in that non-metal column than in the metal column. So if I'm looking at germanium, for example, which is right on that line, if I'm looking at silicon, we're going to treat them as non-metallic. The compounds that they create that we would name are going to follow the non-metallic rules, follow the covalent rules rather than ionic rules. So now we can kind of put it all together. If I have SO3, would I classify SO3 as ionic or covalent? Covalent. So I'm just going to abbreviate. This is covalent. What is its name? Well, I've got sulfur, and I've got 3 oxygens. So the name of the compound would be sulfur trioxide. What about BaCl2? All right, this one is ionic. Easiest way to tell, barium is a metal, chlorine is a nonmetal. We've got a combination of metal and nonmetal, that's ionic. What's the name of the compound? Well, that's where we have to go back to our ionic rules. Ba is barium. Cl is chlorine. And again, for ions, negative ions, we change the ending to IDE. So this would be barium chloride. So we can see in these first 2 examples, the similarities between ionic naming and covalent naming. Both of them had the IDE endings. The difference is, one of the ways that we would know that this first one was covalent, the use of prefixes. Prefixes don't show up in ionic naming. Now I gave you a list here. There is maybe 1 or 2 exceptions on that list. This is a list for a general chemistry class. They have to know a few more ions than you do. But understand, those are kind of exceptions, not the rule. So you're not going to see a dichromate in your problems. You're not going to see dihydrogen phosphate or monohydrogen phosphate in your problems either. So those are kind of going above and beyond what we need and what we would use. All right, letter C. Here's where it gets a little sticky. All of the elements in C are non-metallic. The reason we know it's ionic, though, at least from this purpose, is just that there are too many elements involved. I've got nitrogen, hydrogen, phosphorus, and oxygen. I've got 4 different elements. We haven't taught you how to name anything that didn't have more than 2 elements in it. Our construction wouldn't allow for a naming system for this. We would have no way of really quantifying it. We don't have a prefix, for example, for 12, because there are 12 hydrogens. So where we have to look is we have to look at the list and see, okay, do I see a cluster that is NH4? Do I see a cluster that is PO3? NH4 cluster is at the very bottom. And that's ammonium. PO3 is actually not on this list. You'll want to add it. It is on the list in your book. This is the phosphite. So if you just want to kind of scratch that there on the bottom, PO3, -3. Is the phosphite ion. Since this is an ionic compound, that's as far as we have to take. We just have to name the first ion and then the second one. Ammonium phosphite. We don't have to worry about the subscripts or anything like that. That's all charge balancing stuff. That's what that crisscrossing stuff does. All right, letter D. Ionic or covalent? We've got copper, Cu, which is metal. So we're talking about an ionic compound here. So Cu is copper. CO3, we need to recognize that as a cluster. And if I look on the sheet here, CO3 is carbonate. So copper carbonate is almost the correct answer. What we have to get into here, where is copper on the periodic table? It's a transition metal. What do we have to do with all transition metals? We have to designate their charge using Roman numerals. So what is the charge on this copper that's attached to the carbonate? In this case, it would be 1. How do we know to do that? What are we looking for? Well, we've got a couple of things that we can look at. First of all, we can look at our chart and see that the carbonate is -2 in charge, which matches up with the subscript here, -2, which would mean that the copper has to be +1 to match up with the subscript on the carbonate. So the correct term would be copper 1 carbonate here. For our last one, N2O4, ionic or covalent? This is covalent. We're dealing with nitrogen and oxygen, both are nonmetals. And so now we need to get into our covalent naming conventions. So this is prefixes. I've got 2 nitrogens, so that would be dinitrogen. I've got 4 oxygens. 4 is tetra. And so oxygen gets changed to oxide. dinitrogen tetroxide becomes the result. Again, with that AO piece there, we always drop the first vowel off of it. So if any of the combination of prefix and element name gives us an AO or an OO combination, we're going to drop the first letter, whatever it is. All right. Any more questions about naming before we move off of naming? All right, so where we go from here, the last few pieces of this chapter have a lot to do with kind of looking at things from a molecule standpoint. And so what we are going to start looking at is just the idea of what goes on inside of those bonds. And is it possible to have uneven sharing in a chemical bond? And the answer to that question is yes. And we can structure that overall concept through the ideas of electronegativity and polarity. So let's start with electronegativity. Electronegativity is a number, a value that we assign to a particular element that talks about the ability of that element to draw electrons toward itself. So if that element were to get into a bond, the electrons in that bond would be naturally drawn to this element because it has a high electronegativity. And so if I look at a chemical bond, I can compare the electronegativities of the two atoms in that bond, and I can get an idea of just how evenly those electrons are shared. The closer those two atoms are in terms of their electronegativities, the more evenly the sharing is going to be. The bigger the difference is between them, the more uneven the sharing is going to be. Now, as far as periodic trend is concerned, electronegativity does follow a general trend. And that general trend should make some sense if we think about it. Generally speaking, as we go across the periodic table from left to right, we're going to find that electronegativity increases. And the reason it increases is because as you go from left to right, you're going to find that the atoms, the elements on this side of the table are far more likely to form negative ions than the ones on this side of the table. So if negative is kind of your natural state, you're going to have a general want toward having electrons around you, extra electrons around you. Now, your book puts this term kind of opposite of the way I usually think about it. As you go from the bottom of the table to the top, electronegativity increases as well. Another way of thinking about that is as you're going down the table, electronegativity goes down. So what that indicates is that we have two general trends taking place. As you go up and to the right, the electronegativity tends to increase. As you go down and to the left, it decreases. And so if we were to plot all of the different electronegativities of all of the elements on the periodic table, what we would find is that fluorine is the most electronegative element, and francium is the least. Now, you might be saying, well, what about the noble gases? What about helium, neon, and argon, and so on? Well, you have to remember, this is a bonding characteristic. Electronegativity only applies if a element makes a bond. Noble gases don't bond, so they don't have electronegativity values. Now we can be even a little bit more precise and fine than just general trends. This is called the Pauling electronegativity scale. And in the Pauling electronegativity scale, we can actually put numbers to the value of an electronegativity for an element. And from that standpoint, we can look at fluorine and definitively see that fluorine is the most electronegative element. And it doesn't show row 7 in this graphic, but it does show row 6. And cesium is the lowest on that group. It is the farthest left and down of the elements that are being shown here. But what this kind of table allows us to do is it allows us to break these kind of qualitative ties. So if I'm looking at oxygen versus chlorine, both are one element away from fluorine. Oxygen is to the left, chlorine is below. How do I know which one has greater electronegativity? If oxygen and chlorine were to make a bond together, what one would I expect to have more of a pull toward the electrons? Well, the scale here tells me now it's going to be the oxygen. Oxygen has a greater electronegativity value than chlorine does. It would pull those electrons toward itself just a little bit better than the chlorine would. Now, what this has to do with anything comes into this idea of polarity in bonds. When we talk about polar bonds, what we are talking about are bonds where the electrons are unevenly shared. So here we have an example of a polar bond and a nonpolar bond at the same time. So on the left, we have hydrogen. Hydrogen, when it bonds to other hydrogens, would create a nonpolar bond. And it would be nonpolar because since hydrogen is sharing electrons with other hydrogens, the likelihood of those two atoms sharing evenly is pretty much 100%. They have the same electronegativity. And so what we would find is that if I were going to look at and map the location of those two electrons in that bond, I'd find that they are pretty evenly distributed throughout those two atoms. But if I have something like hydrogen coming together with chlorine, the electronegativity value for hydrogen is 2.1. The electronegativity value of chlorine is 3.0. I'm going to see that because the chlorine is more electronegative, it's going to pull those electrons toward itself a little bit better than the hydrogen is. And the net result is that the electrons are going to just push themselves just a little bit more toward the chlorine side of the molecule than the hydrogen side of the molecule. Not enough to become ionic. We're not talking about a transfer of electron here, but enough that we can definitely notice that the sharing is uneven. It's distorted. It's definitely pushed in one direction more than the other. And the reason why we spend any time talking about this at all is because bond polarity has a relation to another kind of polarity, molecular polarity. And molecular polarity is what explains a lot of the properties of polar molecules versus non-polar molecules. And we'll get to those by the end of this topic today as well. So where do we see nonpolar bonds the most often? We see them obviously because they're covalent bonds. We see them between certain types of nonmetals. And the end result is that we have practically negligible electronegativity differences here. So any kind of bond that is homonuclear, meaning I've got the same atom on both sides, same element on both sides of the bond, that's going to be a nonpolar bond. But any bond where the electronegativity difference between the elements is relatively small, we're talking 0.4 or less, we're going to consider those to be nonpolar as well. So yes, technically chlorine has a slightly greater electronegativity than bromine does, than bromine does. But it's not going to be enough to really see a distortion in the sharing. Yes, hydrogen and silicon have a difference, but it's not enough of a difference to really make any kind of application. Polar covalent bonds, again, also non-metal to non-metal. We see uneven sharing of electrons in these bonds. And where we're talking about electronegativity difference, we're talking about enough of a difference to notice. So generally speaking, we're talking about 0.5 or a little bit better. I'm going to give you some more definitive ranges here in just a minute. Because at some point, this distortion of sharing actually crosses over into the land of ionic. If the distortion is so great that basically the electron is always around one atom and not around the other, then we've gone away from sharing. That's a transfer of electrons. That's an ionic bond that's being made. And so this is where we have to be really careful in just kind of our interpretation. So we can see differences of about a half. That's enough to be considered polar. Difference of 1, enough to be considered polar. Differences of 2, now we're getting into that other territory where we're no longer talking about sharing. When we have a polar bond, we see again, a distortion of the electrons in that bond in terms of how they're being shared. To the point where we can think of one end of the bond as being more negatively charged and the other end of the bond being more positively charged. When that happens, we have what is called a dipole, meaning I've got a positive end and a negative end in the same bond. And the negative end is always going to be on the more electronegative side. We can show dipoles in a number of different ways. The most common ways are these two. Lowercase Greek letter deltas with the sign can tell us the positive side and the negative side. So this funny looking D music note kind of looking symbol here, That's the lowercase Greek letter delta. And a positive on that delta indicates that this is the side that has lower electronegativity. The minus would indicate the side that has higher electronegativity. The other way is to show it using arrows. This is actually the way I like doing it because I don't have to draw all those funny little deltas all over the place. The arrow points to the negative charge. And we usually put a little crosshairs on the end of the arrowhead or on the end of the arrow there to indicate the positive side as well. Ionic bonding is kind of when electron sharing crosses that line between just being distorted to being a full-on theft of an electron. Where we tend to see this the most are between metals and nonmetals. What we tend to see it kind of exemplified in is when we have those large electronegativity differences. And so your book is defining a large difference as anything 1.8 or greater. And so if we kind of put all this in summary here, the electronegativity difference does tell us a lot about the type of bonding that is going to exist. If that difference is 0.4 or less, we consider the bond to be nonpolar. If that difference is somewhere between between 0.5 and 1.8, we consider it to be a polar covalent bond. If the difference is greater than 1.8, we generally consider this to be ionic. One really important note here. If you follow these guidelines, this will answer all the questions in the book. If we're talking about real life substances though, we have to understand that the lines here are not stark. I don't go from, oh, the electronegativity difference is 1.75. Now it's 1.8. This covalent bond just turned ionic. It doesn't quite work like that. The lines here are very fuzzy. And what we'll also notice is that our definitions, metal, non-metal, 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 don't always work out so great for some of these examples. Not to alarm you. That's not the point. The point is more to say there aren't hard and fast rules on this. We're going to use these as guidelines to help us kind of put it into blocks and understand where the differences are. But that doesn't mean every rule is going to be followed to the maximum. Prime example. Aluminum and chlorine. We would think, based upon the fact that aluminum's a metal, chlorine's a non-metal, it would be an ionic compound. When we name it as an ionic compound. But if we go off of electronegativity difference, it's 1.5. 1.5 is not greater than 1.8. By definition, bonding in aluminum chloride is polar covalent. And if you really want to confuse yourself, you can look at the crystallography of aluminum chloride and find that it actually does make covalent bonds. We present these rules as kind of general principles. Sometimes they don't always overlap perfectly with each other. But if we hold fast to the general rule, we're going to be okay most of the time. So this is just a visual representation. Visually speaking, this distortion here, where we sometimes we will use these color maps to help us to show the evenness or unevenness of sharing. So in nonpolar bonds, we can see, generally speaking, the colors here are pretty neutral, even across the molecule. When we see polarity introduced, we usually see a distortion starting to take place, where we can clearly see there's an end that is bigger, that has the higher electronegativity, the negative charge, and a side that is smaller, where the electrons aren't as prominent. And eventually, that leads to a separation. So using electronegativity difference, let's try to identify these bonds into the three categories: nonpolar, polar, or ionic. Now to do this, we're going to have to consult that electronegativity chart. So potassium is 0.8, nitrogen is 3. The electronegativity difference, 3 minus 0.8 would be 2.2. 2.2 would tell us, since it's greater than 1.8, this is an ionic bond. This is what we would expect, given the fact that we know that potassium is a metal and nitrogen is a nonmetal. For nitrogen, we already did this one, it's 3.0. Oxygen is 3.5. Our difference, 3.5 minus 3, is 0.5. 0.5 is right on that low side of polar. Remember, the cut line there is 0.4. So anything above 0.4 we can consider to be polar. Chlorine to chlorine, well, chlorine's 3.0. 3.0 minus 3.0 is 0. So this would be nonpolar. Hydrogen is 2.1. 3 minus 2.1 would be 0.9. Anything above 0.5, or excuse me, 0.4 is considered polar. So hydrogen to chlorine would be polar. So the key aspect of this kind of question is really looking at those electronegativity values, doing the subtraction, and kind of seeing where on the table does it fit. Good.
For like the quiz, will you give us the...
Yes. Yes, that's a table. Luckily, the book is picking ones I know. So that's why I'm going and just doing it without the chart. Otherwise, I would need the chart too. So, what you would need to know you would need to know where the cut lines are. Those wouldn't be given to you. But you know, the test that I just gave you back, the electronegativity chart was on that reference sheet that I gave you for this very reason. All right, other questions with this concept? All right, so honestly, this is the part of the chapter that we're going to try to go through from a 75,000 foot view, because if we start to go too deep into it, we're going to lose ourselves very quickly. So the whole reason we are even mildly interested in polarity from a bonding standpoint, why we care about electronegativity at all, is because of this. We know that certain kinds of compounds are naturally more attracted to each other than other kinds of compounds are. And we can kind of fit the level of attraction between molecules into categories based upon polarity. There are nonpolar molecules that are attracted to each other in one kind of way. There are polar molecules that are attracted to each other in a different kind of way. And then there are ionic compounds, which are attracted to each other in a way we've already talked about, based upon that positive to negative attraction thing. So the reason we went into all of this was to kind of try to give us a framework to understand the concept of polarity overall. And so what this gets us into then is, if I have compounds that are covalent and they are polar molecules, meaning that the molecule itself, not just the bond, but the molecule itself has one of these dipoles, has a positive side and a negative side. Those dipoles will attract each other kind of in a similar way to how ionic compounds attract each other. The only difference is that the attractions are weaker in these covalent compounds than they are in the ionic compounds. And the primary reason there is the degree of charge. Ionic compounds have full-on +1, +2, +3, -1, -2, -3 charges. If I were to measure the charge in a dipole, I might get 0.2, 0.3, 0.5. And that's kind of the big difference between them. That full charge versus that partial charge is going to be the difference between an ionic compound and a polar covalent compound. So dipoles do exist. If we have a dipole that happens to include hydrogen bonded with fluorine, oxygen, or nitrogen, then what we have is a special version of a dipole called a hydrogen bond. And those hydrogen bonds are even stronger than polar molecules are. They kind of fit in that space between polar and ionic. Hydrogen bonds do. Still not as strong as an ionic bond, but a good step up in attraction compared to polar covalent molecules. It is these hydrogen bonds that, if we go back to the previous slide, we're looking at this helix molecule here. Those attractions, hydrogen bonds, are what cause DNA to, well, really exist. They help to make the twisting that we see in DNA. They also help those base pair groups to link up. Why is there a double bond between adenine and thymine? Why is there a triple bond between guanine and cysteine? Because that's how many hydrogen bonds that they make. On the other hand, nonpolar molecules are governed by what are called dispersion forces. These forces are weak. They technically exist, but they are incredibly weak. And so if I start to look at the physical properties of a compound like gasoline, octane, which has 8 carbons, 18 hydrogens, and I compare it to a compound that is a lot smaller like water. Water has much better physical properties than the octane does. It's liquid for a much longer series of time, much greater range of temperatures. It doesn't freeze as easily. It doesn't, well, it doesn't boil off nearly as quickly. There's a lot of things that are good that come with those polar bonds and with that polarity in molecules. So when I look at non-polar molecules, dispersion forces are the only things that keep them together. And so as a result, it's really hard for non-polar molecules to make solids. It's a little bit easier for them to make liquids, but the thing that they always have in common is that those solids and those liquids very easily turn into gas. Take carbon dioxide, for example. Carbon dioxide, we can compress it to the point where it turns into a solid. We call that dry ice. But as soon as you release dry ice from its pressurized environment, immediately it starts to go through a process of sublimation. Immediately goes from the solid phase directly to the gas. Doesn't even stop for a cup of coffee in the liquid area. And that's because the things that are holding that carbon dioxide together just aren't that strong. So some ways that we can kind of categorize, group, and recognize when these kinds of forces exist. One of them is melting point. The stronger the attractive forces are in a compound, the higher its melting point is going to be. If you have weak forces present, that melting point drops very, very quickly. And again, think about what I was just saying about dry ice. Dry ice is got a, well, dry ice doesn't have a melting point, at least not at normal conditions. I can't observe carbon dioxide in the liquid phase at atmospheric pressure. I have to bump up the pressure considerably and lower the temperature. If I compare a polar covalent compound to an ionic compound, we know the difference. Water is a liquid at room temperature. It does freeze at 0 Celsius, 32 Fahrenheit, but it warms up and becomes a liquid relatively easily. Ionic compounds, think about salts. When was the last time that you saw a salt that was in the liquid phase? Doesn't happen very often. Why? Attraction. The attractive forces that are holding those ions together are a lot stronger. And so that's raising that melting point ever so much higher. So again, we can kind of put them into three groups. The solids, the things that we expect to be solid phase at room temperature and at high temperatures above that, have really strong attractive forces. The ones that we expect to see in the liquid phase at room temperature usually have decent attractive forces to each other, usually are polar in nature, especially depending upon when that boiling point is. Substances that have no polarity whatsoever, if we find them in the liquid phase, we know that they are usually volatile. They evaporate really easy. And we can usually tell. You know, if I have something like benzene. Benzene's a liquid at room temperature. I can usually tell that there's benzene in the room because it stinks. Think about some of the other kinds of liquid organic chemicals that you encounter. Aldehydes, ketones, all those organic compounds that we're going to get into in this next unit. If they're a liquid, they're usually pretty volatile. They evaporate pretty easy. You can smell them because, well, they all have odors too. Just as a comparison here, again, looking at melting points, a couple of common melting points for some ionic compounds, all well above room temperature, 800 degrees, 1200 degrees. For those with hydrogen bonds, we can see that the melting point for those, pretty good, kind of in that middle range, a little bit better than the other dipole ones. For the ones that are just dispersion forces, yes, chlorine has a lower melting point than hydrogen chloride. There's another factor that comes into this, it's mass. The bigger and heavier the compounds get, the more natural attraction they have toward each other. And so it becomes hard at a certain point to compare two different compounds to each other if they have wildly different masses. But the idea, again, is very simple here. Greater attraction, greater forces, that's going to impact the physical properties considerably. So how do I go about identifying these? Well, the ionic bonds should be the ones that should be easiest to pick out. I'm looking again for metal and non-metal. There's an example of that. For dispersion forces, I'm looking for non-polar kinds of stuff. So I'm looking generally for, do I have a bond where I've got the same atom on both sides? Or do I have at least two atoms that are really close to each other on the periodic table? I still probably need to pull out the electronegativity values, but I can at least evaluate it that way. Bromine to bromine, that is a nonpolar bond, a nonpolar molecule. This is going to be dispersion. For the others, we could go to the values on the Pauling scale. Let's just assume that for a second that they are all polar. If they're all polar, then what we're looking for is, can we find any of these that have hydrogen bonding in them? How do I identify hydrogen bonding? I need to look for hydrogen with either a nitrogen, an oxygen, or a fluorine. So NCl3, nitrogen trichloride, has no hydrogen in it. Can't do hydrogen bonding. This is dipole. dipole to be more precise. In water, I've got hydrogen, I've got oxygen, I've met both criteria. This is hydrogen bonding. In NH3, this is ammonia. I've got not hydrogen and nitrogen. So this is also hydrogen bonding as well. All right, so this is the last concept out of chapter 6. And like I said, if we try to go too deep into it, we're going to get lost very quickly in the weeds because there's a lot more that goes into it than just being able to identify bonds and stuff that we're not getting into at all here. But if we can recognize and put our molecules into one of those three groups, nonpolar, polar, ionic. The only thing that we have left after that is figuring out if the polar ones also have the hydrogen bonding capability as well. And so we just look at the chemical formula and we see, do we have hydrogen? Is that hydrogen attached to one of those three elements? And if it isn't, then we know it's just regular old dipole. If it does, then we know that it graduates up to hydrogen bonding instead. All right, any questions here in chapter 6?